You know what I should have done back here on example 3, which I forgot about? So we had the graph of the function, the cubic function there, but didn't we find a parabola for the derivative function? And it was like this. I'm going to graph both of them together just so that we can start making some associations that are going to really, really pay off for the rest of the year. And that is, look at where this green graph, which is the derivative of the purple graph, look where it crosses the x-axis right here. So just look at where this corresponds to on the original graph, okay? And then it crosses the x-axis here. Look at where that corresponds to on the purple graph, okay? Now, the other thing was what we talked about in another video. Look at where our derivative is positive right here. And look at where that corresponds to on the original function. Notice that it's going upwards. All of the slopes here would be positive. And then in between these two purple points, like I'm decreasing, and look at where the derivative is. It's all negative right there. Start making those connections. Let's look at for part A. All right, whatever. Find the derivative f prime of x for f of x equals the square root of x. Okay, so there's a graph of the square root. Remember, that's basically half of a parabola that's turned sideways because it's kind of almost the inverse of x squared. Let's get some space going here because I have a feeling we're going to need it. So I'll start just like I started the last one with a limit. No, I will not. I'm going to start it with the notation f prime of x is equal to, now I'll take the limit, as h goes to 0. You can use delta x here if you want. Don't be afraid of it. F of x plus h minus f of x all over h. Do you have that memorized yet? Surely you've done 4,000 problems involving it, so now I'm going to plug stuff in. Yeah. And get the limit as h goes to 0. I don't need the f anymore. I need the square root. X plus h minus f of x is the square root of h. No, it isn't. Square root of x all over h. All right, what do I do? What if I were to just plug in 0? If I plug in 0 here, plug in 0 here, obviously I get a 0 on the bottom, but don't I also get a 0 across the top? Because it would be square root of x minus the square root of x, which is 0 over 0. So I have to fix that indeterminate form. How do I fix it when it's square roots? I rationalize. I need to multiply by a conjugate so I can get that square root stuff on the bottom. So my conjugate's going to be the square root of x plus h plus the square root of x on the top and the bottom. It's our fancy one. We're rationalizing the numerator. And when I multiply this, I want to expand out the top of this. It's as if it's the difference of two squares. The middle term should cancel out very conveniently, which is, why we're doing this technique. Bring down the limit notation. That's not right. That's correct. Okay. So the square root of x plus h times the square root of x plus h just gives me x plus h. The minus square root of x times the positive square root of x gives me minus x. All over, keep the bottom factored, thusly. Okay, and then I think it's time for cancellation crayon because those things disappear. If you want to, you can go ahead and cancel out the h's. I'm going to do that in the next step anyway. I got an h left on the top. I got an h factored out of the bottom. And now my cancellation crayon is going to come in handy once again. And h divided by h is 1, so don't forget that we still have a 1 up top here. Equals the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. So since I have a 1 on top, there's no possible way that I'm going to get like the indeterminate form. It's entirely possible that I still get, let's say, a 0 on the bottom in some cases, not this one, but in some cases maybe. But that's not indeterminate. That just means that it would go to positive or negative infinity or something like that. This one's not. It's not going to happen. Instead, we've got, I can take the limit by just plugging in 0. I don't need to write the lim down again. Plug in 0 for this guy, and I get 1 over the square root of x plus the square root of x, which is the same thing as 1 over 2 square roots of x. What did we find? We found the derivative of our function, which is going to give us the slope at every single point on the original graph. Okay, I'm going to compare and contrast these things for us. Once again, remember that our original function here was the square root of x. So for the square root of x, what's its domain? Well, its domain is, it's not all real numbers. You can't take the square root of a negative number. Well, you can. It's imaginary, but we're ignoring that for the purposes of calculus. So it's just got to be 0 bigger. So it looks like this, 0 to infinity, right? You can take the derivative of, not the derivative, you can take the square root of 0. That's perfectly okay. So let's look about this one. Is the domain also from 0 to infinity, including 0? No, it isn't. And the reason why it's not is because we can't have a 0 on the bottom there. So actually, I got to take this out. So it actually excludes. And this is what I was referring to back on when we were first talking about the derivative as a function. Its domain is a subset of the domain of the original one. We had to take out 0. And let's actually see why we have to take out, well, we can see with the equation why we have to take out 0. Let's see what happens on the actual graphs of the derivative. So here's the original one, square root of x, and then here's the graph of that derivative, what it looks like. Notice that as we approach 0, the slope is getting infinitely big. We got a vertical asymptote here. And the reason why is because as I move from right to left, closer and closer to the origin, this graph is getting steeper and steeper and steeper and steeper. It's approaching some sort of vertical tangent line at that particular point. All right. And then as I move to the right on the derivative graph, you can see that this has got a horizontal asymptote. It's getting closer and closer to 0. And what that's indicating about our graph is that it's getting, less and less steep. It's starting to get as close to horizontal as possible. Would it ever get horizontal? Heck no, that's an asymptote. You can't get to 0. All right. So there is a part B to this, and it is for BC only kids. It is this. Find f prime of x for f of x being equal to the cube root of x. So basically you're finding the derivative of the cube root function, trying to figure out what that is. The process should be sort of similar to what we just hear, but there's going to be an added complication. And that added complication is something to do with this right here. So here was the conjugate. This was the conjugate when it's a square root. I wonder what the conjugate is when it's a cube root. Is it the same thing? I don't know. That's for you to figure out. And we'll talk about that specifically in class. You AB kids, if you want the extra challenge, you can go ahead and give it a go. And we'll see what you come up with.